The Planck Epoch. In the first sliver of time after the universe began, everything we know about physics simply breaks down. Space and time themselves were tangled together in a way no equation can fully describe, and the four fundamental forces we recognize today, gravity, electromagnetism, and the two nuclear forces, existed as a single unified force. Temperatures reached levels so extreme that the usual laws of general relativity and quantum mechanics stopped making sense when applied together. This period lasted an almost unimaginably short span, far less than a trillionth of a second, yet physicists believe it set the fundamental rules that everything afterward would follow. Whatever happened during this brief window remains one of the biggest open questions in modern physics, since no experiment on Earth can recreate conditions anywhere close to it. Cosmic inflation. Moments later, the universe underwent a burst of expansion so extreme that a region smaller than an atom stretched to the size of a grapefruit in a fraction of an instant. This rapid stretching smoothed out the early universe, ironing out any large irregularities that might have otherwise torn it apart or left it wildly uneven. At the same time, tiny quantum fluctuations were stretched along with space itself, planting the seeds that would later grow into galaxies and galaxy clusters. Without this sudden expansion, matter would likely be clumped unevenly, and the large-scale structure of the cosmos would look nothing like the web of galaxies astronomers observe today. Inflation also helps explain why the universe looks roughly the same in every direction we look, a uniformity that would be difficult to account for otherwise. The Quark Epoch. As the universe cooled from inflation, it became a seething soup of quarks, electrons, and other fundamental particles, all too energetic to bond into anything larger. Temperatures were still trillions of degrees, far hotter than the core of any star, which meant particles collided and separated again almost instantly. Photons, gluons, and other force carriers zipped through this dense plasma, keeping everything in a constant state of motion. Only as the universe expanded and cooled further did conditions finally allow quarks to bind together instead of bouncing apart. This transition marked one of the first moments where matter began taking on a more structured form. The Hadron Epoch. Quarks bound together in groups of three, forming protons and neutrons for the first time, which are collectively known as hadrons. These new particles collided constantly with their antimatter counterparts, and when matter meets antimatter, both are annihilated in a burst of energy. For every billion or so of these annihilation events, one extra particle of matter survived without a corresponding antiparticle to cancel it out. That small imbalance, still not fully explained by physicists, is the reason stars, planets, and people exist at all today instead of a universe filled with nothing but leftover light. Neutrino decoupling. Around 1 second after the beginning, neutrinos stopped interacting with other matter and began drifting freely through space. Before this point, they had been tightly coupled to the surrounding plasma, bouncing off particles constantly. Once the universe expanded and thinned out enough, neutrinos simply stopped colliding and moved outward on their own. These ghostly particles still travel through the universe largely undisturbed today, forming a faint cosmic neutrino background that scientists have only recently begun to detect using highly sensitive instruments. Their early release marked one of the first times any particle type moved independently through the young cosmos. Bang Nucleosynthesis. Within the first few minutes, protons and neutrons fused together to create the earliest atomic nuclei, mostly hydrogen and a smaller amount of helium, along with faint traces of lithium. This process only lasted about 20 minutes before the universe cooled and thinned out too much for fusion to continue. The precise ratios of these light elements created during that brief window still match what astronomers observe in the oldest, most primitive stars they can find. This agreement between prediction and observation is considered one of the strongest pieces of evidence supporting the Big Bang model as a whole. Recombination. Roughly 380,000 years later, the universe had cooled enough for electrons to finally bind with atomic nuclei and form stable, neutral atoms. Before this point, light couldn't travel freely because photons kept scattering off free electrons drifting through the hot plasma. Once atoms formed and free electrons were swept up, photons were released to stream outward in every direction, no longer trapped by constant collisions. That ancient light still reaches us now, stretched by billions of years of cosmic expansion, and we detect it today as the cosmic microwave background radiation. The Dark Ages. With no stars yet burning, the universe entered a long stretch of near-total darkness that lasted hundreds of millions of years. Hydrogen and helium gas drifted through space, slowly clumping together under the gentle but persistent pull of gravity. There was no starlight to illuminate this gas, only the fading afterglow of recombination cooling further into the microwave range. It was a quiet, patient period, one where the raw material for everything that came later was simply gathering itself into denser and denser pockets, waiting for the right conditions to ignite. The first stars. Eventually, gravity pulled enough gas together in these dense pockets to trigger nuclear fusion, giving rise to the very first stars. These early giants, sometimes called population 3 stars, were far larger and hotter than most stars burning today, some possibly hundreds of times the mass of the Sun. They burned through their fuel remarkably fast and lived comparatively short lives before collapsing in massive explosions. Their deaths seeded the surrounding gas with heavier elements, like carbon, oxygen, and iron, that had never existed anywhere in the universe before that point. The Era of Reionization. Light from these first stars and the early galaxies that followed them began stripping electrons from neutral hydrogen atoms scattered throughout the universe, a process astronomers call reionization. This gradually cleared away the cosmic fog that had blanketed space since the Dark Ages, allowing light to travel more freely across greater distances. The process didn't happen all at once, but unfolded gradually over hundreds of millions of years as more and more regions became ionized. By the end of this era, the universe had become transparent in much the same way we observe it to be today. Galaxy formation. Over the next several billion years, gravity drew stars, gas, and dark matter together into the sprawling structures astronomers now call galaxies. Smaller galaxies merged and collided with one another repeatedly, building larger galaxies piece by piece through countless cosmic collisions. Our own Milky Way likely formed this way, gradually absorbing smaller neighboring galaxies over an extended stretch of time. This slow architectural process shaped what's now known as the cosmic web, a vast network of galaxy filaments and voids still visible in modern sky surveys. The Stelliferous Era. This is the age the universe currently sits in, defined by the ongoing birth and death of stars across countless galaxies. Nebulae collapse under gravity to form new stars. Those stars burn through their nuclear fuel over millions or billions of years, and their remnants often trigger the formation of still more stars nearby. Galaxies like our own continue slowly evolving, occasionally merging with neighbors and reshaping their structure in the process. This era is expected to continue for trillions of years, far longer than the universe has existed so far, before the raw material needed for star formation finally runs low across the cosmos. The Degenerate Era. Long after star formation finally ends, the universe will be filled mostly with the burned-out remains of stars, white dwarfs, neutron stars, and black holes. These dim, dense objects will drift through an increasingly cold and dark cosmos, no longer producing the light and warmth that once defined galaxies. Occasionally, two of these remnants may collide or merge, producing brief flashes of energy in an otherwise silent universe. Some theories also suggest that protons themselves, the building blocks of ordinary matter, may eventually decay during this incomprehensibly long stretch of time, slowly dissolving whatever structure remains. The Black Hole Era. Eventually, black holes will become the dominant objects remaining in the universe, slowly evaporating through a process known as Hawking radiation. This decay happens at an extraordinarily slow rate, meaning even the largest supermassive black holes will take a span of time vastly longer than the current age of the universe to fully disappear. As they evaporate, they release faint radiation until nothing is left of them but a last, quiet burst of energy. Once the final black hole vanishes, almost nothing structured will remain anywhere in the cosmos. The Dark Era. In the final stage, physicists currently theorize, the universe will consist of a thin, cold scattering of particles spread across an ever-expanding void. Without stars, black holes, or any meaningful structure left to interact, energy will be spread so thin that almost no activity remains possible anywhere. Photons and stray particles will drift for what amounts to an eternity, growing ever more separated as space continues stretching outward. This quiet, near-empty state represents one possible ultimate fate of everything that ever existed, a universe that ends not in fire but in silence.